Welcome to the Flyback Transformer design portion of the tutorial. What we're going to go through quickly is how I went about designing the Flyback Transformer, which is really the heart of the grid tie inverter. But before we do that, I have to show you this paper because this is where everything is derived from. So if you Google grid tie inverters flyback, you're going to come up with a lot of different papers on the subject, a lot of articles, papers, research. This is the best one, and I've downloaded them all and I've read them all. And this was the one that motivated me to do the project because it is concise. It starts out giving you definitions of all the acronyms, and gives you an introduction, explains what's going on, and then gives you the formulas to help design the transformer. Goes through the analysis, the theory of operation for the modulation. So everything is here, right? So this is the paper I used to generate my spreadsheet to help me make this. So all the formulas on this spreadsheet are derived directly from that paper. So the way this spreadsheet is laid out, the gray is where all the calculations are done. Okay, so you don't want to type directly into the grayed out regions. Okay, the white is what you want to use to enter in variables that you can change. Okay, the light blue is just units and attributes, and then the remarks are just in the light yellow here. So just the takeaway here is don't type into the gray because that's being calculated. Okay, so what I want to do is we'll start off here quickly and say, okay, I want to minimize leakage inductance, right? So in the course of determining the transformer, I want to make sure I'm following these rules, right? So I want the fewest number of turns possible. I want to fill up the entire bobbin with both primary and secondary, right? So ideally one layer for primary, one layer for secondary. I want to minimize the insulation tape between the layers. So you lay down the secondary, you put some tape, you lay down the primary. So you want to keep that tape as minimal as possible, but still staying safe and not shorting things out. You want to use a small diameter wire size versus a large diameter wire size. So always smaller is better. So smaller, multiple strands. Okay, and then finally you want to wind the turns neat and tight. You want it should look good when you're done winding it. It should look really good and tight, no gaps. These are all things that are going to minimize this leakage inductance. It's going to make your life a whole lot easier if you decide to build this. Okay, I just included some pictures of this is my transformer. So here's your gapped core. Okay, so these are two halves, and the two ends fit together nicely, but in the center there's a gap. Okay, and for this one the gap is about 30 thousandths of an inch, and that's where the energy is being stored. So during the charging phase, the energy is stored in the gap. The gap is everything. Okay, now just looking at what we have, these values represent the breadboard that I have today. So in looking at this, so how did I arrive at this? Well, there's two ways you could approach this. You could approach this by changing values to get the results you want here, and then take what you get out from the transformer and work that way. Or you could decide, hey, what kind of a transformer could I reasonably make following these rules, and then adjust these values so I can reach that. Okay, so I took the latter approach, right? So I didn't spend any money on this project. I used everything that I had laying around. So I had certain wire laying around, magnet wire. I have a few different sizes. So based on my core size and the lengths and everything, I was like, what can I fit? So I knew I could do around 7 turns and maybe 24 turns. So that's what I adjusted these numbers to give me basically this. Okay, so the things that I had control over. 30 volts is what I chose because of eventually when I do this part 2 with the solar panel, my operational range for the solar is between 24 and 33. So I chose 30. My grid is 230 volts. I'm choosing a switching frequency of 36 kilohertz based on several factors. One is the PWM resolution. Another is, it allowed a 20 millihenry output smoothing inductor to really smooth up the waveform. So I decided, and then finally the switching loss, right? Because the higher you go in frequency, the more switching loss you get, right? So 36 was for me the top end that I was willing to go to. And then I knew that I wanted 7 turns and 24, so I knew my turns ratio, so I could set that. So what was left is to play with this guy. And I think what I did is I actually came up with 16, right? And I said, okay, if I wind this with 7 and 23, I'm going to get around 16. So then when I finished winding the transformer and measured it, I ended up actually being 7. So everything plays together here. Okay, so at the end, what pops out is, hey, I got 216 watts of output power with the maximum duty cycle, right? And it's important, this box, if you leave it blank, it calculates what the maximum duty cycle will be for the given design. And you want to leave it blank when you're playing around with different parameters. It's only when you think you've reached where you're happy that you now could type something in there, and then you can lower this, right? Just go to 0, right? If I turn off the PWM, it goes to 0. So that's the purpose of this, to see what kind of range you're going to have, right? So by leaving it blank, I can see what the maximum is. So the maximum is 216 watts. Right now you'd say, wow, that's pretty good. I can get 200 watts. Paul, why is it only a 100-watt inverter if you can get 216? Well, the reason is, if you look at two things, right? So the first thing you look at is, okay, the ID peak is 37.5 amps, okay? Well, if you looked at my earlier Instructable on inductor saturation meter, I use that to show me what this transformer was going to do, what's the performance of it. So I wound the transformer, right? And then I tested it. And I know that this is what I'm getting. So you can see this is a typical hard knee. It's a ferrite core, right? And the inductance stays fairly flat, and then all of a sudden it drops off. So I want to stay in this region, right? I don't really want to go much past this region. So this would be the absolute maximum I would want to go to. And that's 29 amps, right? So, and ideally I want to operate here. So I really want to operate less than 26.5 amps to stay well within the linear range of this. This is way over. And on top of that, it's showing me that if I want to maintain a maximum flux density of 375 milliteslas, this is showing me that it's over, right? So I'm exceeding everything. So there's no way this can run at 200 watts. It just won't work, right? But that's okay, because I'm not going to run it at maximum duty cycle, right? I'm going to run it somewhere around here, right? So I can get 120 watts now, right? And I can still stay within my targets, right? My current dropped down to 28 amps, right? So if I go back here and I say, well, is that okay? Well, if I go to 28 amps, that's somewhere around in between here, which is 26.5 and 29, somewhere right around here. So yeah, that's okay. I'll operate there. I got a little bit of margin here if it goes up a little bit, I'm okay. I'm right. So that's pretty sweet. I'll operate there, right? So that's how I built the prototype.